Um, I have several homeworks to hand back, but I wanted you to look at that one. There you just got, if you look at the back box, what was it? Number 16. Um, I guess I want you to understand what I require and I want you to use your noggin a little bit here. Now that's an indeterminate form. This problem is somewhere else in the paper, or maybe on another homework, but do you agree that's negative infinity times 0? You have to show it's indeterminate, use L'Hopital, cha-cha-cha. You with me?
Yeah.
Okay. It is most definitely not the case that when I give you that problem, I expect you to do L'Hopital. What should you do? It's the definition of the derivative. It is the alternate definition of e to the x at 3. So I expect you to say, oh, that's e to the x. No work at 3. All right? Can't we all agree, or actually I'll remind you, that every limit definition of the derivative will always, 100% of the time, come out 0 over 0. That is the idea of the derivative, of taking change between 2 points and taking both differences down to 0. Every definition of the derivative that ever existed, every limit ever, was 0 over 0. Now, if you always use L'Hopital on every definition of the derivative problem, you're going to be wasting a lot of time. That's silly, okay? So, just so we're clear, indeterminate form, use L'Hopital, show all the good work. Definition of the derivative, not L'Hopital, just do the derivative. Understood? Okay. With that in mind, then, let's talk about yield. Actually, I felt like as I was teaching this last class, this first part of the notes was, well, that's all right. What is a derivative? Tell me one way to talk about a derivative. Slope, okay, slope, I agree, tangent slope, which you find by taking slope between 2 points, decrease slope, and taking the points closer and closer together. That's interesting you say that, because nobody in the other class said that. They all said instantaneous rate of change. But secant slope is fine also, or tangent slope, not secant slope, tangent slope. Either way, in both cases, the definitions of the derivative take the change between 2 points and then take the points closer together by the limit. The change between 2 points is some fashion of the change in the function over the change in x. And the points closer together is always the limited fashion. And they're all different notations, but it's all change between 2 points getting closer together, so it's going to just change it one point, right? Would you give me one possible way to estimate the derivative at 3? You could say it's approximately f at 4 minus f at 2 over 4 minus 2. That is acceptable. That's using the idea of the blank definition of derivative. You're approaching from both sides, yes? So what definition are you using? Alternate is at a point, so it's not alternate. From both sides, in the exact same fashion on either side, it's almost the mirror image of ice. Thank you. Golly gee, bullet pushing. The symmetric definition. Okay? Couldn't you also use the 3 itself with 4? That's the definition of the derivative at a point. But why use 4 and 3? Couldn't you use 3 and 2? Yes? Do you agree? So on a multiple choice, any of those 3 possibilities would be there. They would never put more than one of those in a multiple choice. because there's no preference over the other. However, if they had a table where 5 was present, for example, would it be okay to use f of 5 and f of 3? No. What part of the definition of the derivative does that violate? Take the change between 2 points. Is it doing that? F of 5 minus f of 3 over 5 minus 3. Is it doing this? Getting as close as possible to the instant you want. That violates that idea. Okay, that's a violation of the limit idea. All right. Now all these, we use the average rate of change to estimate the instantaneous rate of change. But it's often the case, like today, with differentials, you go the other way. You use instantaneous rate of change to estimate average rate of change. Today is the opposite. Okay, so here we go. When you estimate change with differentials, remember differentials are just dy or dv or dA, depending on what you're trying to estimate changing. The differentials are Leibniz's little microscopic delta. D is an abbreviation or approximation of delta. It's just a microscopic delta. So that's where that D comes from. Differentials are microscopic differentials. You with me? All right, cool then. Here we go. Here's the deal. If I were to separate these two guys so that I could just estimate delta y, how much does y change, then I could move this bad boy over and say delta y is like, well, I guess you could say it's like the rate of change times an amount of change in x. Now that is this. Actually, I wish this is what I put in my notes. This is the big idea. If you're going to remember one thing about today's lesson, first of all, why are you so lame? But second, it would be this. This is crucial. True change is estimated by how is it changing at that instant. Now let's be clear. Unless you're talking a linear function, it is going to be an estimate. Imagine f looked like this, yeah? And I started here at the original point. Now, if I were really interested in the true change from this y to this y, that here, that's the actual change in the curve went under from that point to that. You with me? If I use calculus, I'm going to be saying, well, I'll go based on how it was changing at this instant. And I'll say I'm going to take how much I expect to change x by just the same way, but y will change by a little different. Now, that would be the idea of based on how much it's changing at that instant times an amount of change in x gives me amount of change in y. It'll be a good estimate. As long as the point's not too far away and the curve isn't too bendy, it'll be a good approximation. Now, here is an example of both the type of problems you see and the work I demand. So it goes a little something like this. The radius of a spherical balloon is 3 inches. Use differentials to estimate how much the surface area will change if the radius grows by a 1/4 inch. Now, I think you all know that we could find the true change by just saying, you know, what's the surface area at 3, and what's the surface area at 3 1/4, and take the difference. That's the true change in surface area, right? We're going to estimate using differentials. Now, in math and calculus and in engineering, differentials are actually used to estimate change because they're a little, first of all, cleaner in power. You're dealing with derivatives, so you're going to be one less power. And they're actually a pretty doggone good statement. So you'll do this quite a bit in science and engineering. I have a lot of homework here. I'll get this. All right. Of course, that's why that stacks still. But the idea goes like this. If I start with a 3-inch balloon I increase the radius by a 1/4 inch, the surface area obviously will change about how much by, and approximate it using calculus, all right? Anybody want to take a stab at it? By changing the radius a 1/4 inch, you think you'll change the surface area by? No guess. Okay. You think. All right, so here's the idea. How much the surface area will change? That is the true change in area. Now I'm going to estimate that with the differential for area. How much the area changes by depends on two things. The rate of change, or the relationship of change between the area and the radius, and how much I change the radius by. Now that's just like I had on that last slide. Okay, dy is like the derivative times an amount of change in x. In this case, there's no y's and x's. dA is like the derivative times an amount of change in r. I would expect you then to report your derivative. If the area is 4 pi r squared, then a prime is 8 pi r. Add an r, or at a previous point in time, add an r of 3. And then the dr is how much I will change the radius by. I will change the radius by 1/4 inch, all right? So that would be something like 8 pi times 3 over 4, or 6 pi. This should have units. What are the units on this? Inches squared, okay, because we're talking about change in surface area. So just by a little 1/4 inch change in the radius, the surface area would change by 18-ish square inches. All right, now let's talk error. This is often used to estimate error in calculation. Now, if you take a measurement and then use that measurement to make some other calculation, then that new calculation will also have error in it. Do you agree? That's called propagated error. When you build a second answer based on a possible erroneous first answer, you're going to get propagated error, or error built on error. In this case, we all looked at its radius. Yeah, I think on your paper it says radius. Does it?
Yes.
Okay, sorry, I changed my notes. I have to change my slide. Okay. So everybody has this ball, and they looked at it and they took a guess at what they felt the radius was. And they all felt it was 12 centimeters, or the average of all the guesses was 12 centimeters, right? But because we're all guessing, there could be as much as a 1/2 centimeter off, or the standard deviation. So based on differentials, estimate the possible error that could result if we then used our guess at the radius to calculate the volume. Now we're trying to estimate the true error, or how much the volume could be off by. That's delta V. And we're estimating with the differential dV. dV comes from two things. The rate at which the volume is changing at the instant, or V prime, times the amount that the radius could be off by VR. I will look for this in every problem. That step should be there every time you do a differential. Every time. Okay? Then you report your V prime. What's the derivative in this case, because it's a volume of a sphere? If volume is 4/3 pi r cubed, then V prime is 4 pi r squared. At what r will we calculate that rate of change? 12. And the dr is 0.5. Now, is r, how much we're off by, is that 0.5 too much or 0.5 too little? Plus or minus. It's actually plus or minus, because I don't know if that's above or below. Okay. Now, that wasn't plus or minus in the previous problem. How come the previous problem didn't have plus or minus? It grew. It was said grow, so there's no plus or minus. Okay. All right. So if we calculate here, we have 4 plus or minus rather 4 pi times 12 times 12 divided by 2, I suppose. So what do you get there? 144 times 288 plus or minus 288 pi cubic centimeters. To me, that was surprising. I have pretty good math sense, but that surprised me. The radius being off by 1/2 of a centimeter resulted in the volume being off by almost 900 cubic centimeters. Okay, now, the next part of this concept then is, okay, so my area is about 288 pi cubic centimeters. The follow-up question then would be, is that a lot? Well, if I measured a baseball and I was off 288 pi cubic centimeters, was I off a lot? Yes. But if I measured the sun and I was off 280 pi cubic centimeters, am I off a lot? No, that's practically zip. So wouldn't you agree then the answer to that question is that a lot of error is, it's relative. It's relative to what you're measuring. So more often than just finding error in an engineering setting, you would find relative error. As it relates to that which you're measuring, is the error very big or not? So relative error is the comparison of your error measurement, which is your differential estimate, to the actual thing you're measuring. So in this case, if I wanted the relative error for the previous problem, then dV to V, without respect to sign, dV we said was 288 pi. The volume is 4/3 pi r cubed at a radius of 12, is that right? Okay, so the pi's drop out, and 288 times 3 over 4 and a bunch of 12s. Calculator schmalculator, am I right? No. Yep. So that's, let's see, those 2 12s will go into that and leave a 2, and that's a 1, 2, and that's a 4. So it feels like 1/8, yeah? As a decimal, what is it, 1/8 is decimal? Not even think about picking up your calculator. 0.125, okay? And then, last but not least, it's also pretty common that rather than express it as a decimal, you express it as a percent. And so you'd say, in terms of percent error, this is 12.5%. Okay? Now, depending on your field, you would say, man, that's a lot of error. Oh, man, we really nailed it. It would kind of depend. I imagine most fields don't. Are you with me? Okay, last but not least, you can use differentials in more of a numerical, mathy kind of setting to do estimates, a lot like you would use a tangent line. In fact, there's a ton of overlap here. When you use differentials to estimate a new value, then you take an old value, let's call it the y new is y old plus change. And that'll be estimated by y old plus dy. Okay, we'll estimate the true change by dy. Now, in a case like this, then, the idea is that you're estimating something ugly by starting at someplace pretty. So the y new is the square root of 47. And you'd say, well, that would be like if we started at the square root of 49 and changed it some. If we started at the square root of 49 and then changed it some, obviously there would be some change by going from 47 to 49, we could estimate that by saying that's like 7 plus some differential change, or the rate at which the curve changed at our good point. Now that is the same as 7 plus I guess I need to identify my variables. So let's let y equal f of x be the square root function, yeah? So the differential idea you communicate is the idea of the differential is the rate of change times an amount of change in x. A rate of y changing for x changing times how much x is changing gives you how much y is changing. And in this case, the derivative is 1 over 2 root x. And do I do that at 7 or 49? What's the x value? Yeah, 49 is the x value, 7 is the y value. And dx, is that which we're going to change x? It's either 2 or negative 2. Which is it? Which one makes sense? Am I going to decrease in value when I square root due to the derivative, or the square root of 47? Yeah, obviously I'm going to change x. And that's because our old x was 49. Our new x is 47. So delta x or dx is a decrease. Okay? From old to new, or start to new. So I get something like 7 plus 1 over 14 times negative 2, or 7 minus a 7, or 6 and 6. Wait. It's the exact same thing you do with the test chart. Exactly the same answer. There's some difference in notation, obviously, but it's the same estimate. Okay? I believe that you are now ready to try it on your own or with your math amigos. Math amigos.
You should release an album this year.
You think? Yeah. If I could sing it all, I should be a songwriter, really. If I could get some busy enough to sing those songs.
Can you get the ukulele orchestra?
Yeah. Are you guys looking for new material? Original material?
Sure. You're welcome to
Yeah,
email the guy if you
that'd
want
be
to.
a real rough sell.
He's
It's really great song. Oh, man.
Gary, he likes weird songs, so
Really?
he'd be down for
Maybe
it.
we do the show.
You never know if you don't try.
Yeah, exactly. Throw it out there. Yeah, the units. So it's DD, so it's just D's units. So what are D's units? It's right at the back of it, Steve. 3.7. Eight, maybe? Hey. Did you get 4.88 with that appropriate work? And what are the units? Feet. That's feet. It's by going 1 mile per hour more, how much will the distance change? You're looking for the distance and the distance, stopping distance units. And that's feet. By going just 1 mile an hour more, your distance stop will be approximately 4.88 more feet. Let's see. I got 2/15 relative error, so the percent error. Did you get 13.3 or 13 1/3%?
Yes.
Yay. All right. Okay, so is it clear enough? So how do you approximate delta y? dy, and how do you find dy? Y prime or f prime of x times dx, the difference. Okay, cool. Questions on last night's homework? How did the 20 go? Do you have 20 down? Okay, this is an important skill for next week. This is going to lead to delta epsilon proof next week, which is one of the hardest calc 1 topics you'll see. It's delta epsilon proof. Okay, and whether you know it or not, here you're proving that the limit as x goes to 2 of 2x minus 1 is 3. But that's for later. Okay, did this go okay or no? You need a walkthrough. Okay, here's the deal. You assume this and prove that has to happen as a consequence. When you prove an if-then statement, you assume the hypothesis and prove the consequence. So let's assume that x minus 2 is less than a 10. Your goal is to show through accepted math that must follow into f of x minus 3 has to be less than 2/10. So you need to show that that can be eventually, through accepted math rules, taken to that. Now, for students starting off, I would strongly recommend if you look at just the step right before that, it's helpful for students. F of x in this problem is 2x minus 1. That's a little easier to see how you're going to get there. I need to go from there to there. What's one thing I can do to change the look of this to make it look like that? Multiply by 2. Okay, so I can multiply by 2. Do you agree? Oh, shut up. I will finish on Monday. You can turn it in Monday. That I definitely want. The yellow I want. The extra practice I want. Okay? The key is online, so if you need help, judiciously use the key. Have a lovely weekend. Thank you. Thank you. Thank you. Thank you. Where to get those on? What? Yeah, why? Did you just say, no, I don't want it back? You just take it.
I don't have it. Evan has it.
Why does Emma have it?
Do you think an extra week would be helpful? You know, you can't say no to that. It's like, well, I think it would be
But then he would have
next year.
destroyed you and been like,
But I
well,
thought he
you
was
could
talking
have
about
had another
next year, and
week
then
to
he
be
was like,
better.
okay, well, since you think that, here's your paper. I was like, no, I don't actually want it back. It's just saving my stress.
So you're just gonna stick it in the folder and keep it till next
I'm
week?
gonna leave it in my folder for a week.
That's funny. All right, I got that. That's done. Uh-oh, that just stopped recording.